At the smallest scales of spacetime, particle interactions are chaotic. When two particles collide, their potential pathways instantly branch out into thousands of possible geometric configurations. For over half a century, physicists organized this chaos using the diagrammatic expansion developed by Richard Feynman. This graph maps Feynman's complexity scaling. Moving from tree-level to multi-loop configurations, the required diagrams undergo a factorial explosion, scaling at big O of n factorial times L to the 3L. For higher loop gravity calculations, this growth creates a computational dead end, eventually exceeding the limits of calculation. To move past this wall, the search for a solution has shifted away from diagrammatic expansions towards an entirely different mathematical arena. This alternative framework, celestial holography, was developed by physicists like Sabrina Pasterski to move the analysis of scattering amplitudes to the boundary of the universe. Andrew Strominger provided the foundation for this by mapping the symmetries of four-dimensional flat spacetime directly onto two-dimensional conformal symmetries on that boundary. Instead of tracking interactions inside the bulk of spacetime, we analyze correlation functions on the celestial sphere, the spherical sky at infinity. Here, Daniel Toupin proved that L-loop integrands are already encoded within tree-level data, arising mathematically from L+1-fold shadow discontinuities. This suggests a massive shift in how we calculate the universe. We no longer need to build multi-loop diagrams. We extract loop integrands directly from tree-level boundary data. To verify Toupin's theorem, we have to translate standard quantum variables into the language of the celestial boundary. The mathematical bridge is the Mellin transform. It maps a four-dimensional momentum vector to a coordinate, extracting its conformal dimension, delta. These boundary operators sit on a vertical line in the complex plane, where the real part of delta equals 1. This is the principal series. On this boundary, a symmetry exists called the shadow transform, which relates the conformal dimension delta to its shadow, 2 minus delta. If celestial holography is a valid duality, this geometric shadow symmetry on the boundary must correspond to a physical operation in the four-dimensional bulk. The mechanism for that correspondence is lemma 3.2. In momentum space, a unitarity cut severs a loop line, placing the particle on shell as a delta function. The Mellin transform reveals this on the celestial boundary. As energy approaches zero, the integral resolves into a mathematical pole exactly at delta equals 1. For a full two-particle unitarity cut, both internal lines of the loop are forced onto the principal series. When delta 1 and delta 2 are both 1, their sum is exactly 2, reproducing the shadow pole condition required by the boundary theory. We can then extract the amplitude using the Sikotsky-Plumel formula, which takes the discontinuity across that specific pole. Finally, an inverse Mellin transform converts the spectral data back into the exact one-loop measure used in momentum space. The proof is mathematically identical. Severing a loop in four-dimensional spacetime is the same operation as calculating a residue at a shadow pole on a two-dimensional boundary. This collapses the task of computing massive bulk structures into the much simpler task of reading boundary data. To find the one-loop four-point integrand, we simply take the double shadow discontinuity of a 6-point tree amplitude. This data terminal shows the results of Toupin's validation. The shadow-derived integral matches the standard Feynman scalar box integral to exactly 16-digit floating point precision. The method scales recursively. 2-loop integrands arise from 8-point trees, and 3-loop integrands arise from 10-point trees. The intractable diagrammatic explosion is gone. It is replaced by a linear sequence of algebraic integrations. These discoveries ground the geometric legacy of Roger Penrose and his work on light ray boundaries in a new computational reality. For decades, we assumed loop amplitudes were independent quantum corrections that had to be added to fix a theory order by order. But Toupin's work reveals that the complete quantum architecture of multi-loop spacetime is already encoded within the analytic structure of tree-level boundary data. These results establish celestial holography as a structurally complete description of quantum gravity. We do not need to calculate the infinite fluctuations occurring inside the universe. The boundary already knows the answer.